We're on section 11.4, comparison tests. This is example 1D. We got the series of square root of n over n squared plus 1. So comparison test, that's potentially something we could use. We also have a limit comparison that I've introduced to you at this point. So either one, the b sub n process is kind of the same. Also note that you have to have your a sub n greater than 0, which we've got going on here. So playing the game with the dominant terms, we have our numerator, just one thing there, down low n squared plus 1, n squared's dominant. So let's compare with the square root of n over n squared, which simplifies to 1 over n to the 3/2, which is something we know about because the series of 1 over n to the 3/2 is a p-series, which I conveniently put in the excerpt again from the formula sheet having to do with the p-test. In the convergent versus divergent column, we look at the p here, which is in this case 3/2, and it is greater than 1, which means we got a convergent series here. So at this part of the game, it's like, do I want to do limit comparison or do I just want to do comparison test? So I'm going to go back to comparison just because I want to give you another example here. It seems out of the two techniques, it's one that students seem like they need the most help with. So here is my b sub n, which again I'm writing in the unsimplified form because it's more easily comparable with my a sub n. And now I'm going to play the comparison game. I got the same thing on top, square root of n, so that's equal footing, but down low I got a slight difference, n squared plus 1 versus n squared. So comparatively, the denominator of a sub n is bigger than our b sub n, so I'm just going to label them big and small in that way to get the relative differences in here. And then when you multiply, or divide by a number that's bigger compared to one that's smaller, you get a smaller value. So then I can insert my inequality and start to do my analysis here. So going back to our b sub n, that series square root of n over n squared which we've simplified to 1 over n to the 3/2 is convergent. So is our inequality going the correct way, that we have a bound on our a sub n term where the series of the b sub n is convergent? Yes, this inequality is going the correct direction and it is bounding it. So I can make a conclusion using just the comparison test that our series is convergent. So quickly, if you did the limit comparison test, just to show how that would have played out, our b sub n would be the same. And here we have this limit as n goes to infinity. Even though you avoid the inequality, sometimes students struggle with just the algebra involved with the limit comparison. Is usually a little bit more intense here. So this is pretty routine where we have our multiplication by the reciprocal. In this case we had the square root of n's cancel, then we got to do limit. Fortunately this one is actually not too bad. I chose to use L'Hopital's here and I got 1. So because 1 is greater than 0, then we just characterize our b sub n series is convergent or divergent, and then our a sub n series will do the same thing. So this one, either method worked. Let's just move on to the next one and final example actually. Example 1e. I guess I could have just called this big example, but it's called example 1. we got the series of 4n squared plus n over the third root of n to the 7th plus n to the 3rd. So notice one little difference here is we've got n equals 2. No big deal, you pretty much treat this like you normally would. Don't feel like you have to do something totally different here. When we're doing comparisons, potentially you'd want to start at n equals 2 because that's what the series is for, but besides that, you just kind of do this as usual. So my b sub n, for either my limit comparison or comparison test, I'm looking at the dominant terms again. On top that's 4n squared, down low this is going to be the third root of n to the 7th. So we simplify that, and we get 4 over n to the 1/3. So we got the constant there for, but besides that, we got a p-series, and our p is less than or equal to 1, so this is the divergent case. And here's the excerpt from the formula sheet. Alright, so I'm going to do limit comparison test here, or at least show it here. If you have one to choose, usually the limit comparison test works better and more often, but it can be kind of hairy with the algebra and stuff sometimes, so, and with having to, again, doing a limit where the comparison test, there wasn't any limits required, but it does work more often than the direct comparison test. So some caveats here, but anyway, I just did the a sub n over b sub n thing. Again, you could do the b sub n over a sub n. Multiply by the reciprocal, and I got what we have here. So just kind of getting a little look at this, we do have infinity over infinity. Notice that L'Hopital algebra would be a mess here because we'd have, well, I guess I could distribute the n to the 1/3 here. Down low, I would have to do the chain rule, and that would actually get pretty messy. That'd be hard to avoid. So anyway, it's like, well, maybe there's another way. So we're actually do some algebra here. This is a good chance to review how you would do some algebra here with n goes to infinity, and all these powers floating around on the top and the bottom, and then that root as well. So you want to multiply by 1 over n to some power. The way you choose that power is you choose the highest power in the denominator. The equivalent of, like, the magnitude of the power of the denominator is going to be 7 over 3. So even though you can't do the algebra to take the third root of n to the 7th separate from n to the 3rd because there's plus between them, in terms of magnitude of the power in the denominator, that's what we got, 7/3 power. So that's how I choose the denominator there of n to the 7/3, and overall the top and the bottom. Now we do all the algebra and good things are supposed to happen. So let's see that. So I'm going to write this out. Limit as n goes to infinity, and we're going to have 4 n to the 7/3 divided by n to the 7/3 plus n to the 4/3 over n to the 7/3. Next thing, I'm just going to put my 4 out front here, and I have my third root, which is the same as this 1/3 power, and then the n to the 7th comes inside the root. So we're going to have n to the 7th over n to the 7th plus n to the 3rd divided by n to the 7th. So I kind of did quite a few algebra steps there, but again, the 1/3 power is the third root. So when you have the same root here, I can put them underneath and distribute what would be the 1 over n to the 7th. Okay. Reduce each of those fractions, we get 4 plus, and then here we're going to get n to the -1, which is 1 over n. 4 third root, 1 plus 1 over n to the 4th. Now it still looks kind of weird, not simplified, but because we multiply by this really special choice of the power, then that guaranteed that I could evaluate this limit directly in this step after we simplified all the fractions. 1 over n as n goes to infinity goes to 0. 1 over n to the fourth goes to 0. The rest of this stuff is constant. So what we get here is 4 over 4 times the third root of 1. And this is just going to be 1. So, limit comparison test. We're just trying to get a value that's greater than 0. And since our comparison sum, general term b sub n, was divergent, then we can conclude our series that we care about, or our a sub n series, is also divergent. And this is by the limit comparison test with our series of n over, or 4 over n to the 1/3. So just a tip here, if you had tried direct comparison with the same b sub n, this one you actually wouldn't have been able to get anything that was useful, whereas the limit comparison test did work in this case. Alright, that's it for 11.4.